So I will talk about some results on linear convergence for Douglas-Rachford splitting in ADMM. And we will essentially, I will focus on the Douglas-Rachford case. And also we will not, we will actually show linear convergence by showing that the Douglas-Rachford operator is contractive under the assumptions that we will be discussing. And this is actually work. Okay, yeah. So I was a postdoc with Stephen like 4 or 5 years ago. So most of this work was done while I was a postdoc there at Stanford. Then we solved a number of these cases to get contraction factor for this operator. And now recently we revisited one of the cases with a PhD student at the same department where I am at Lund University in Sweden, Carolina, and also Adrian Taylor, who is with Francis Bach in Paris. Okay, so the algorithm is then the only unconditionally convergent frugal without lifting and resolvent splitting. So this is actually, yeah. So this is, we can call it this, or we can call it Douglas-Rachford. It's either. But again, we solve monotone inclusion problems, AX plus BX. Here we've seen that set. And we have the iteration like this, just like Ernest also had, and Jonathan yesterday, and others. We call it Douglas-Rachford splitting for all parameters alpha between 0 and 1 in this talk. And R is the notation for the reflector resolvent, and J is the notation for the resolvent. So I'll just introduce this operator, TDR, which is the Douglas-Rachford operator, which takes us from xk to xk plus 1. And in general, we know that this is non-expansive and alpha averaged. And we will talk about conditions under which this mapping is contractive. And I guess you can, you know this essentially, and it is, you have on A and or B properties such as strong monotonicity, co-coercivity, and Lipschitz continuity that will give you those properties of TDR. Okay, so I will give you a formulation of an optimization problem that will actually find such a contraction factor for the Douglas-Rachford problem, for the Douglas-Rachford operator. And so if we just some sloppy notation, let TDR or script T be the class of Douglas-Rachford operators where we have these combinations of stronger properties in A and B, strong monotonicity, co-coercivity. A and or B has some of these properties. We just very sloppily let TDR be this class of operators. And then we can find a contraction factor of this the worst case contraction factor from this class by solving an optimization problem on this form. So essentially, we want to maximize the ratio between Tx, the norm Tx minus Ty, over x minus y. So this will give you, if this is less than 1, this will give you a contraction. And then we say that T is in this class of Douglas-Rachford operators with A, B having stronger properties, and then X, Y in Rn not equal. So it turns out that with Stephen, I worked on, yeah, let's go here, an analytic or operator theoretic approach to solve essentially this optimization problem. In some cases, some combinations of stronger properties of A and B. And then more recently this year with Carolina and Adrian, we have worked on the optimization-based approach where we actually solve this optimization problem directly, even though we have this tricky, let's say, constraint. It's possible to rewrite this in a way such that it can be solved by a very small-scale semi-definite program. And this is work that we have done, which is extending work of Dorit Tebui that did talk about this performance estimation problem, or performance estimation framework. It's called PEP or PEP in this paper from 2014 in math programming. And this has been extended by Adrian Taylor, also math programming 2017. They have been considering convex problems with gradient methods. for gradient methods. So now in this talk we're considering these operator splitting methods more generally, or Douglas-Rachford more specifically. Okay, so essentially the outline of the talk will be that I will first talk about some background. So the operators that we will have, the reflector resolvents will have stronger properties, and I will talk about some graphical representations for such operators, or these properties. Then I will talk about the cases of Douglas-Rachford splitting, or the different combinations of A and B and stronger properties of those, in which we have contraction factors. And some of these are analytically derived, and I will describe some ways to arrive at these. And then I will also discuss how to derive them from solving this optimization problem that I just posed. Okay. So just to get you into the graphical representations that we'll have throughout the talk, essentially. So the first is a representation of a Lipschitz continuous operator. So in this case, it's a contractive operator with contraction factor beta. So Tx minus Ty will end up somewhere within this gray shaded circle if x minus y is here. We can also relate it to if there is a fixed point, which it is since it's contractive in this case. We can relate where Tx will end up in relation to the fixed point. We just replace y with a fixed point, and we get an inequality that can be depicted like this. So Tx will be closer to the fixed point than x is. Okay. The next operator is an averaged operator. So it's an average or weighted average between a non-expansive operator and the identity operator. So depending on the averaging, this averaging is between 0 and 1. So depending on what averaging we use, 0.5, 0.25, 0.75, we get different possibilities on where Tx minus Ta may end up. So for 0.5, we will end up in this mid-gray circle here. And with respect to fixed points, Tx will end up in this within this circle here. Okay, and of course, non-expansiveness is the white thing, the full circle. Okay, so in order to show the one of the convergence rates in for the analytic methods, which is also used in the performance estimation framework, we had to introduce a concept of negatively averaged operators, and it's, I mean, a straightforward concept. It is that the minus the operator that we have is averaged, and we call that negatively averaged to have a name for it. And to represent this in graphics, we just flip the figure along the vertical axis to get something like this. So if we start out, for instance, here, if we have a negatively averaged operator, it will end up Tx will end up for alpha equals 0.5 within this circle here. Okay, so that's negatively averaging. And then the final thing that I will have a picture for here is a co-coercive operator. So it's co-coercive if beta t is firmly non-expansive or 1/2 averaged. And this is the corresponding figure. So scale it by beta, and you will get firmly non-expansive, half averaged. And then we see also that it implies, in this case, in the general case, 1/beta Lipschitz continuity. Okay, so Douglas-Rachford contraction factors. So there have been lots of convergence rate results on Douglas-Rachford splitting in ADMM. And here we list only a few of them, that essentially they are general under these properties. So essentially satisfying these properties and attaining sharpness or partial sharpness, essentially, you could say. So this is a list of combination of properties of strong monotonicity, co-coercivity, Lipschitz continuity, applied to monotone inclusion problems or optimization problems. So the first two are from optimization problems. Then co-coercivity and Lipschitz continuity, those properties coincide. And then the last four are from monotone inclusion problems, where the two co-coercivity and Lipschitz continuity properties are different. Okay, so O1, we have both stronger properties, strong convexity and smoothness of the function f, and A is the subdifferential operator of that function in A, and B is just the subdifferential operator of some convex function. In the second optimization case, we split these two properties into the two operators. So A is strongly convex and B is smooth. Then we do similar thing for the monotone occlusions, but we have both coercivity and Lipschitz. So in the first two cases, we have both stronger properties in one of the operators. And in the last two, we have split strong monotonicity and coercivity, strong monotonicity and Lipschitz continuity between the two operators A and B. And so this column here tells us if the rates in these references are sharp or not. So for this case, there are sharp rates for all parameters, essentially, in these two papers. O2, there are partially sharp rates in paper 3 here. It's sharp under these assumptions, but only for some of the parameters in the algorithm. So for big enough relaxation parameter, essentially, it's sharp. M1, M2, where both of the maximum monotone cases are in one of the operators. There are also sharp rates. When they are split, there are partially sharp rates. Turns out that this rate and this rate is the same. And this M4 it just recently came on archive by Walla and Leven, where they had sharp rates when in addition this Lipschitz operator is linear. Is that right? Yes. Yes. OK. So we see a pattern here that the sharp rates are for the cases where both stronger properties are in A, and B is just, non-expansive or a subdifferential of a convex function. When the properties are split between the two operators, we don't have sharp rates. And there is a reason for this that I will try to convince you about or show you in graphics, essentially. So essentially, the reason why the cases where we have both stronger properties in one operator is easy is that the other operator is non-expansive, so it doesn't do anything. So essentially, when you know the properties of RA, where A has stronger properties, you also know the properties of the Douglas-Rachford operator, essentially. When you split the properties between the two, none of them are non-expansive. They have stronger properties, and there will be an interaction because of the composition between the two operators. And this is much harder to sharply characterize the convergence factor in that setting. OK. So I will start out by showing one of the easy cases, which is M1, how to obtain a contraction factor in that case, essentially. So A and B are maximum monotone, and A is sigma strongly monotone, and 1 over beta co-coercive. So both properties are in one of the operators. So what properties do we get for the reflector resolvent under those assumptions? So if we start with the strong monotonicity, it's easy to show that the resolvent is 1 plus sigma co-coercive, this figure. Then to go to the reflected resolvent, we multiply, let's say, this by 2, shift by -1, and we get something like this shape here. And it is also very straightforward to show that the reflector resolvent is negatively averaged due to strong monotonicity of alpha with this factor. So we get negative averageness of the resolvent. So we assumed also co-coercivity of the operator. This gives a resolvent which is averaged with this factor. To get the reflector resolvent, we multiply by 2. So this one multiply by 2 to get to that one. Scale by -1 to go back here, and we get another averaging. And it's also, the factor is beta over 1 plus beta, so the averaging factor for RA. And this means that RA is negatively averaged, and it's also averaged. So essentially, negatively averaged gives us this thing, averaging gives us this thing, which means that since it has both of these properties, RAX must end up somewhere within this, this shaded region here in this two-dimensional example. And it turns out that when you do the math, you get that RA is contracted with this factor. And when you do the geometry in this two-dimensional case, it turns out that this is also contracted with the same factor. And then you directly, now you analyze one of the reflector resolvents, and because both stronger properties are in one of them, you directly get a convergence rate for the full Douglas-Rachford operator, or the contraction factor, which just adds these relaxation parameters alpha on top of the contraction factor of RA. So this is a sharp rate in that case. Okay, so that was one of the easier cases, let's say. So now let's go to which was called case M3, which is we have the same assumptions, but it's now split between the two operators. A is strongly monotone and B is co-coercive. So of course, the reflector resolvent of A will now be negatively averaged, and the reflector resolvent of B will now be beta over 1 plus beta averaged from before. Okay, so now the analysis, which was not sharp for all parameters in 3 that we had before, shows that the composition between this negatively averaged operator and the averaged operator is negatively averaged. So composition negatively averaged and average gives back a negatively averaged operator on this with this factor. And it turns out, as I will show you now in a number of pictures, that this is a conservative property, which gives us a conservative estimate for the convergence rate in that case. Okay, so if we choose sigma equals 1 and beta equals 1, the strong monotonicity and co-coercivity constants, we will get 0.5 negative averageness and 0.5 averageness of the two resolvents, reflector resolvents. And the result from thesis that the composition is 2 over 3 negatively averaged. And these are graphics that show you, that will show you where a point in the composition may end up. So first we have the circle for the negative averaging. So after the first RA, we apply it, it will end up somewhere in here. So now we add where may it end up. If we have worst case, we follow this circle. So if after the first reflector resolvent, we end up here. Where will we end up after the second one? So then it will be somewhere within this dashed region. So we do this for all of the circle, well, a discrete set of points on the circle, let's say. And we get something, a shape that looks like this. Okay, so this is well, roughly the shape where the point may end up after we have done this composition. And if we compare these two, if we approximate this with something which is negatively average, which was this circle, we see that we have conservatism in this region here. We said it is negatively average, but we cannot end up in this region here. Okay, so this is one shape for 0.5 average and 0.5 negatively averaged. So different shape may be like this. If we choose different sigma and beta, in this case 0.2 and 7, we will get negatively averaged of 0.83, which is whatever you get this circle, which has crosses all over. And then RB is average with 0.88. So for each of these points, we have a circle which gives the averageness. And the composition will be somewhere within this, whatever it is, shape here. And we see again that we have conservatism when characterizing this with a negatively averaged operator, or approximating this with this property, it's conservative, for instance, here. Okay. So, yes. Okay. So when we have a negatively averaged operator, in this case, the composition is negatively averaged, and we do an average map of that. So now it's a triple averaging, let's say. Then it's easy to show that the convergence factor, a convergence factor of this is given by that expression. So you get an averaging of the negatively averaged operator, and the contraction factor will be given by this expression. It turns out that this rate is sharp for all, but not for some, but not all alpha, as I hinted before. So when we do averaging of this shape that we had, it will shrink, and it will move closer to the original point. So in this case, we see that sigma equals 2, beta 7, the same as we had before, and alpha equals 0.95. the contraction factor that we get from this analysis is the black one. And it turns out to be sharp for this choice of alpha. But if you choose a smaller alpha, we see that the gray thing, which is the negatively averaged approximation of the operator, touches the black thing, which is the contraction factor. And this turns out to be not sharp because we see that there is nothing from the original operator that touches the boundary of the thick circle. And again, if we reduce alpha even further to 0.7, we see that there is a region here where it's all white. So where we may end up do not touch where we actually, the circle for the contraction factor. So this region here is really a source of conservatism in these estimates. Okay. So what can we do about that? Is it possible to actually get sharp rates in this setting? So what we do is we go back to the original optimization problem that we have, and we actually try to solve this explicitly. And we reformulate this problem into an STP. I will show you all the steps, how to do that, essentially. And we will get an equivalent problem which will give us a contraction factor for this mapping. So the problematic part here is, the most problematic part is, of course, the operator class inclusion problem that we have to replace somehow. And I will go through, 10 minutes? OK, thanks. I will go through a number of steps to replace this. And the key steps will be the interpolation conditions that I will describe, and that the inequalities that we will replace this by with will be so-called Gramian representable. And this, again, this is an extension, let's say, of the work by Bourret-Tibouy and Taylor, Hendricks, Glinier, and also others. OK. So this problem, we can replace this by just explicitly stating the Douglas-Rachford steps. So we go from x, apply the reflected resolvent, get x1, apply the reflected resolvent, get x2, and then we do the averaging to get x plus. And x plus is then tx, let's say. So we just replace the operator t by reflected resolvents on A and B. We do the same for y. So we start at y, we arrive at y plus. And now we have essentially not gained anything. We still have this constraint that A is any strongly monotone operator and B is any 1/beta co-coercive operator. So we haven't gained anything by this reformulation. But with this result, we can do something. So this is called, Adrian, in their paper, they call it for interpolation conditions. So we stick to that terminology. So if we define, this can be more general, but we define two duplets. So we have duplets x and x1 and y1. And we have this condition that relate the points. Then this condition holds if and only if there exists a sigma strongly monotone operator A such that x resolvent applied to x is x1 and reflected resolvent applied to y is y1. So there's an if and only if between this and the existence of a sigma strongly monotone operator A such that we can generate x1 and x2 by the reflected resolvent of that operator. OK. And similarly, in the co-coercive case, we have, in this case, x1, x2, y1, y2. And we have this condition, which is very similar to the previous one. We essentially flip a sign and replace sigma by beta inverse. Then this condition holds if and only if there exists a 1/beta co-coercive operator that whose reflected resolvent takes x1 to x2 and y1 to y2. So, and actually similar if and only if statements can be derived for all properties that are circles, essentially, in the diagrams that I showed before. OK. So this will give us a simplification of the problem. So we can actually remove everything that is in red here. This one, that one, and this thing by only these two constraints. So the interpolation condition gives us something that takes away most of the tricky parts in this optimization problem and replaces it by, well, simple things, let's say. So now,
is this a same? I mean, are they equivalent or is this a relaxation?
Yeah, it's the same cost.
Okay, so the interpolation condition is exact.
Yes, so you get the same cost. You get the same optimal cost. Yeah, exactly. Okay, so of course, now we have this, which looks easier. To the next step, just plug in x plus and y plus to get this formulation. Yeah, so nothing strange happens there. And now it's the second part of the reformulation into a convex program. That is the Gramian representation. And if we look at all the terms here, this term, that term, and everything here, they are, in this case, norm squared things. And you could potentially have scalar products. I mean, in these things, you will get scalar products. Because of this structure that I have, they can be represented in Gramian form. So we introduce Gramian on this form. So we say that this is the x minus y norm squared. We had scalar product x minus y, x1 minus y1, and so on. So this is independent of the dimension of x and y. This Gramian matrix is 3 by 3. And it's positive semi-definite by construction. So essentially, we can reformulate this one to a trace of some matrix A0 times G, where essentially this A0, it essentially picks the elements that we're interested in from here. Yeah, to get the same, yeah, to get this one out of that essentially. So this can be done for all of these. You just construct AO, AS, A1, and A2 to pick the right correct elements of G so that they correspond exactly to whatever we have here. So with this Gramian representation, we have now reformulated the original operator inclusion problem to a problem on this form, which is these are linear in G, and this is just a semi-definite constraint. Okay. So now what we want to maximize is, okay, we look at the constraints. We see that they are positively homogeneous of degree 1. We can scale them by a positive constant and nothing changes. And this is independent of scaling, the cost. So we can ourselves decide the scaling because the problem is scaling invariant. And we set the scaling to be 1. So we set this one to be 1. And we get the problem on this form, which now is linear besides a 3 by 3 semi-definite constraint. So we have gone all the way to a very small convex program to solve this. And we can also show that by employing dual variables to these problems, we can get a dual problem on this form. And in this case, we minimize tau. We have non-negative lambdas. We have an S matrix which is negative definite, where in this case the S matrix looks like this. So we can solve that problem. And we have strong duality if the circles have an interior, roughly, and maybe in other cases as well. Okay. So there are a couple of conclusions that we can draw from this formulation. So the obtained rates are sharp, so there's no relaxation. The Gramian 3 by 3, which means that worst cases are one-dimensional, two-dimensional for Douglas-Rachford splitting. We can draw the conclusion that the optimal convergence rate, how it converges towards a fixed point, is the same as the contraction factor of the operator, which is not necessarily true, but in this case we can show that it is true. We can show that worst cases for these assumptions is independent on if we consider the monotone occlusion or the convex optimization problem. The worst cases are linear, two-dimensional and linear. And in the exact case that we have been considering, we can get this analytic solution, which is either that thing, if the worst case is 1D, or it's this thing, which is a bit more hideous, if the worst case is 2D. So we'll just show you a couple of examples where the worst case is 1D and 2D. So in this case, we do the same thing again, alpha equals 0.95. The worst case is here, and this is on the same, I mean, this is one-dimensional worst case because it's just on this axis. We don't care about whatever happens in this direction. And the factor is 0.9. If we shrink it to 0.89, we see that we have white space here, white space here. So the worst case factors is somewhere here. So it's two-dimensional. And in this case, we get the square root expression, which gives us a factor of 0.82. And in this case, a smaller alpha, the same sigma and beta still. We get the worst case, which is, again, one-dimensional. And it's attained on this side here. And we get the sharp rate in that setting as well. And of course, this is not applicable only to GR. It's to all operator splitting methods where you have these types of properties. You can do the same formalism, and you can draw kind of the same conclusions, essentially. So we have a preprint on the way on this topic, and these are the other works that I was referring to throughout the talk. Okay, thanks for your attention.